webinar is an introductory webinar. I want to expose you to basically what are the typical types of engineered wood products out there, what do they look like, a little bit about how are they made, and how are they used. It's not an in-depth webinar. We're going to have subsequent webinars where we get into the nitty-gritty of each one of these products. But for right now, we just want to sort of cover the basics. And at the end of the webinar, hopefully you'll be able to identify the common types of engineered wood products, a little bit about their production, the primary uses, and what type of information to gather if you come across these products in the field, or you see them on a set of design drawings or something like that. So again, what are they? How are they made? What are they used for? And what to look for? So a quick overview: wood is engineered wood products are made from wood in various forms, and they're bonded together with adhesives. And the most common products that we're going to cover today are structural panels, structural composite lumber, wood eye joists, Glued-Laminated Timber, Cross-Laminated Timber, and structural insulating panels. So a little overview on wood. As you all probably know, wood is orthotropic, and therefore the properties vary with the direction, and typically wood is strongest along the grain and weakest perpendicular to grain. And since engineered wood products are made from wood, they too have different properties depending on the orientation and direction of load. So the first group of products we're going to cover is wood structural panels. This is your plywood and your OSB. First, a little bit about plywood. It is the original structural panel. OSB came sometime later. But it's basically made out of several veneers or plies that are peeled from a saturated log using a lathe. And the veneers are dried and into sheets, typically 4 foot by 8 foot. If you go to Home Depot and you go to the plywood aisle, you're going to find 4 foot by 8 foot sheets. You can get other sizes, but it's a special order item. Again, it's made out of veneers or plies, and those veneers and plies will be graded. You don't have to read this what's on the screen, but just to show you that they do grade the veneers based on the amount of knots and naturally occurring defects and so on, A being the highest grade and D being the lowest grade. Typically for plywood, the two face veneers will be of a higher grade than the inner veneers. And the way it's laid up is typically, the sheets are 4 foot by 8 foot, and the two face veneers will be oriented with the grain along the 8 foot direction, and then the inner plies will be alternating orientation 90 degrees to one another. So if you had a 3-ply piece of plywood, the two outer veneers will be in the same direction, and the one inner veneer will be direction 90 degrees to that. If you had a 5-ply, it would look pretty much like the picture you see on your screen right now. And alternating the plies provides dimensional stability and increased strength. Higher grade plywood panels can be sanded for a better finish. The edges can be milled with tongue and groove. It's pretty common, but they can also do shiplap edges. But the picture on the left is what you commonly see. And you usually see tongue and groove for floor sheathing, but you can see it in roofs as well. It comes in all kinds of thicknesses, but commonly 1/4 inch to 3/4 inch is pretty ubiquitous, but you can get thicker sizes. And just as a side note, it used to come in 1/4, 1/2, 5/8, but more recently you're starting to see 19 30-seconds or 15 30-seconds. And just FYI, 15 30-seconds plywood is a 1/2 inch. So if you spec 1/2 inch plywood and you come out to the site and it's 15 30-seconds, you don't have to reject it. It's basically equivalent, and you're starting to see more of these 30-seconds of an inch measurements. So that was a little bit about plywood. This is OSB. It's very similar. It was introduced in the 1970s and really caught on. It's a little bit cheaper to make and buy, and it comprises about 60% of panel production today. But the idea is the same, except instead of veneers, they have wood strands or chips, and they orientate them in a mat so that the top and bottom mats of these strands or chips will be oriented along the 8 foot direction, and then the mats in between the two face mats will be oriented 90 degrees, pretty much like the little graphic is showing you on the screen there. So very, very similar idea to plywood. And just like plywood, you can sand it, you can put tongue and groove edges. The thicknesses are, it's the same type of deal. And the sizes are again, 4x8 is ubiquitous, but you can get bigger sizes if, it's a special order item. So characteristics for both plywood and OSB. Again, cross-laminating the plies creates a more dimensionally stable, stiffer, and impact-resistant panel. And again, the strong direction is oriented along the length, like the 8-foot direction, and the weak direction would be along the 4-foot direction. And the little graphic there on the right, the top picture is what you commonly see, where the panel is perpendicular to its supports, which can be roof rafters, roof trusses, floor joists, wall studs, or whatever. And that is considered the strong direction. You can orientate it the other direction, as shown on the bottom picture there, but that's a weaker direction, and we'll get into a little bit more about this in a second. Typical uses, as I said, you see it as floor sheathing, walls, and roofs. In this picture here, you see they're using OSB for the walls, they're using plywood for the gable roofs. Very, very common. Again, it's typically oriented 90 degrees to the supports. And in addition to sheathing, it can be used as a diaphragm or a shear wall to handle wind loads, seismic loads, and so on. It is an engineered product, and therefore it'll have some kind of marking or stamp on it. There's dozens of stamps. So here's a few examples, but basically the stamp tells you what you have. And this slide here, a picture of a real stamp. This is plywood, and there's all kinds of information on this on the stamp. But what I wanted to really point out was what they call the panel grade. And in the photo there, it says rated sheathing. We'll get into a little bit about what that means later, but you can also see other terms such as underlayment or sturdy floor, or sometimes instead of a rated sheathing, they'll just tell you what the face veneers are. For example, you might see B-B ply form or BB ply form, which is what the concrete industry typically uses for their concrete forms. The next important piece of information is what they call the span rating. And usually it's one number slash another number. In this example, it's 32/16. And the first number represents the maximum span of the supports or the spacing of the supports when the panel is used as roof sheathing. And the second number is the maximum spacing of the supports when it's used as floor sheathing. The little red box there is also telling you how thick it is, and this is 15/30 seconds. So, people would typically just call this 1/2-inch plywood. And then the other piece of information I'm pointing out is what they call the bond classification, which is either exterior, exposure 1, or interior. That's basically the performance of the glue, the adhesives used to bond the plies together. Exposure 1 is typically what you see most often, but you can get exterior grade plywood or interior grade plywood. For most construction, you see exposure 1. It's a waterproof glue, and if you've ever seen a house go up, they'll sheathe the roof, and before they get the roof shingles on and whatnot, it'll probably get rained on a few times. Well, exposure 1 can handle that kind of moisture, but it's not intended for like a marine environment or something like that. So exposure 1 is what you commonly see. You don't have to read all this, but basically from the stamp, you can go to a document. This is from APA. APA is used to be called the American Plywood Association. And now they call themselves APA, the Engineered Wood Association. But anyways, you can go to some of their design guides and what the red box is showing you there. For example, the stamp I just showed you was rated sheathing, exposure 1. And it'll give you typical uses of it, what kind of sizes or thicknesses you can get it in. Can you get it in OSB? Can you get it in plywood? And the red box, showing you some of the other panel grades that you can see, such as sturdy floor or CC plugged and so on. And so from the stamp, you can go to a document and start getting information about that specific product. And again, APA is like the big certification agency out there. There are others such as TICO, but APA is by far the most common rating agency out there. You can go on the website and you can download all kinds of good information about the plywood and other products. We'll get into that as well. So again, from the stamp, you need the stamp to find out the properties. Otherwise, you don't really know what you have. So based on that stamp, you can go to a table such as this from the APA panel design specification. And for the picture I had up before, 32/16 rated, if you look at the top half of the chart on the left-hand side, that red box, third one down, 32/16, and you can read across and you can pull off all these design values based on the laminations. And if you look at the top of the chart, there's two red boxes, stressed parallel to the strength axis, that's the strong direction, and they're stressed perpendicular to the strength axis, that's the weak direction. So again, you got to pay attention to that because it will have different properties depending on how it's oriented. But, and there are other charts for bending strength, shear, rolling shear, but the point is from that stamp, you can go to a document such as this and pull off all the properties that you need. As I said, typically you see sheathed walls, not just sheathed just to keep the weather out, but they can also be used as shear walls or diaphragms. And basically a shear wall is nothing more than a stud wall that's sheathed, and based on the number of studs, the size of the studs, the grade of the stud, the size of the thickness of the sheathing, the grade of the sheathing, the number of fasteners, the spacing, and so on, you can determine the capacity of that shear wall. And NDS provides tables for this. IBC also provides tables for this information. And those tables look, pretty much like this. Again, you don't have to read all this, but I just wanted to point out that from that stamp, you can, and the thickness, you can go into a table like this and, find the panel you have, the thickness you have, the fastener spacing, fastener diameter, and you can pull out allowable shear forces, which are typically in pounds per foot, for these panels, whether it's used in seismic applications or wood applications, or wind applications. So you don't have to do all kinds of complex analysis. They provide these tables based on testing, and it's very quick to pull out your design values. So again, APA is the big guy in block, but there's also TICO, and you can go to their websites and you can pull out or download all kinds of good information about these products for free. So check it out. This slide is showing some real-world examples. This was a multi-unit, I think it was 4-story residential structure in Jacksonville. It had all kinds of water infiltration. Basically, the sheathing was all decayed. And just a few photos. What you're seeing on the photo on the left is essentially stacked shear walls. Again, the plywood or the OSB has been removed, but it's basically just a stud wall sheath. And those steel straps you're seeing, the vertical straps are transferring uplift forces from a shear wall on one floor to the shear wall below it, and then on down to the foundation. And the horizontal metal straps there are transferring shear wall forces around the openings. In this case, a pair of doors. But this is pretty typical of what a shear wall looks like. This is another job, again, multi-unit residential in a suburb of Chicago. Here, the roof structure was steel trusses, and then it was sheathed with plywood. And what the photo on the left is showing is the plywood is curling. And plywood and OSB, it's pretty dimensionally stable, but it will warp with changing moisture content, especially in a hot, humid location like an attic. So in order to control warping, you have to fasten it down and adequately. In this particular case, that wasn't done. Either they didn't use enough fasteners, or the fasteners missed the truss, or so on, and the plywood will warp and will curl. The photo on the right, problem there is pretty obvious. When you butt two pieces of panel together, it should happen over a truss or a support so that you can actually fasten it down. And here, I don't know what they were thinking, but they were way off the mark by about a foot. And so therefore, this panel has no structural support along the edge, and that's obviously a big no-no and has to be corrected. And you can correct this with blocking, installed perpendicular to the truss, which I think is what we did, and then fasten the plywood down to that blocking, which is then fastened to the two parallel truss cords. So pretty common what you see out in the field. So that was panels. Next group of products is what they call structural composite lumber, SCL. And there's three major products. We'll get into that in a second, but just as a broad overview of SCL, it's very similar to panels. It's wood in various forms, either veneers or strands or chips, in the case of structural composite lumber, that adhere together with adhesives. And again, the point is that it produces, the engineering process, production process produces a more dimensionally stable, more consistent product. by reducing naturally occurring defects and so on. So here are the three types: parallel strand lumber (PSL), laminated strand lumber (LSL), and laminated veneer lumber (LVL). A little picture of what they look like. And just as a side note, you can nowadays they're trying to treat these products just like they do for solid sawn lumber, and you can get these products treated to resist decay and insect attack. Also, you can rip them down like you can any 2x10 or whatnot, but the manufacturer does limit what you can and can't do with this, so you have to check the manufacturer's literature to see how you can, the limitations of these modifications. All right, so the first type of SCL we're going to cover is laminated veneer lumber, LVL. The most common, at least the one I see most often. It's essentially like a plywood beam. So it's veneers, but they're orientated vertically. And so very similar to plywood, a picture of what one actually looks like with the manufacturer stamp. And they're normally used for headers and for beams. For roofs, you see them used as valley rafters or hip rafters. I've seen them as floor framing if you want to span, somewhat longer distances. Typically, you can get them in greater depth than you can solid sawn, which, for southern pine is 12 inches, and for some of the other species, 14 inches deep. Which is pretty hard to get, but for LVLs, they can go much deeper, up to 24 inches deep, and maybe even deeper for some manufacturers. But the standard thickness is 1 3/4. That is the only thickness they come in, and they're pretty strong compared to, like a #1 grade of lumber, typical modulus of elasticity 1.9 to 2.2, bending stress 2600 to about 2900. So you're getting towards the upper region of what solid sawn can do. If you want to get something comparable, you're probably looking at dense, select structural #1 dense type lumber, or machine evaluated lumber, or machine stress rated lumber. So it sort of competes with that upper echelon of the solid sawn products. So that was LVL. The next type is parallel strand lumber, or PSL, and it's marketed as a timber alternative. So instead of specifying, an 8x10 timber, which may be hard to get, you can specify an 8x10 or probably a smaller PSL since it has some higher strength. We'll get into that in a little bit. But so you typically see them used as headers, beams, columns, some more major structural members. You're probably not going to frame your floor with PSLs unless, you have to span some really long distances, I guess. But you don't normally see that. And again, Paralam is the brand name for Weyerhaeuser, who again I think is the only producer of PSL. But this is what it looks like. The photo on the right shows you the cross section. It's basically a bunch of strands orientated along the length of the beam or column, and all glued together. They come in different widths. You can get quite wide, about 7 inches wide or so, and the depths vary. Again, 9 1/4 to 18. You might be able to find some other sizes, but they're they're generally used for major structural members. As the picture on the left is showing, it's used as a column and a beam, which is supporting other framing. And the strengths are quite high. Ease on the order of 1.8 for columns and 2 to 2.2 for beams. Bending strength 2400 to 3000. So it's getting, again, it competes with the upper echelon of machine stress rated or MEL lumber, and again it's marketed as a timber alternative. The next type of SCL is laminated strand lumber, LSL, and it's sort of like if LVL was a plywood beam, LSL is sort of like an OSB beam. It's again kind of the same idea. They're taking strands and they're laminating them together in a vertical orientation. And you don't see this as often, at least I don't, but you see them a lot. If you do see them, they're usually used as headers, beams, rim boards a lot, and sill plates. You tend to see it used or specified. In this picture, they're being used as columns, but typical sizes, as opposed to LVL, which only comes in 1 3/4 or thickness, these come in a variety of thicknesses, and again, depths, from 3.5, which is like a 2x4 equivalent, to about 18 inches deep. And again, some manufacturers might have some sizes outside of this range, but in general. And the strengths, while not as high as LVL or PSL, are still quite good. Pretty high E, they're up to about 1.8. and bending stress 1700 to 2300. So still pretty strong stuff as compared to what you typically see number 2, lumber, solid sawn lumber. So again, the key with all these products is the stamp. If you find the stamp, you'll know what you have. Again, TSL is only made by one manufacturer, so you typically don't see much more on the stamp other than Paralam or Weyerhaeuser or something like that. But for LVLs or LSLs, the stamp will contain other information like 2.0E or FB 2900 or something to that effect. But you have to find the stamp. And from the stamp, you can go to manufacturer's catalog. This is from Weyerhaeuser. And based on that stamp, you can pull out all the properties. Weyerhaeuser makes LSLs, LVLs, and PSLs. Some manufacturers, they might, well, no one else makes PSL, but point is you have to go to the manufacturer's literature to pull out the design values. They're proprietary products. You cannot visually grade them like you can a 2x10. You have to find a stamp to know what you got. And you can drill holes in these products to run conduit and mechanical or whatever. And that is allowed, but it does have limitations. And you have to go to the manufacturer's catalog to get the limitations. I think this one is from Weyerhaeuser, and they all might be similar, but they'll all be a little bit different. So you have to go to the manufacturer to find out the extent of holes and notching or whatnot that you can do to these products. So this was a job, again, multi-unit residential in the suburb of Chicago. Here they used triple LVLs actually to make a header beam over a garage. And they had all kinds of leakage, so all kinds of decay was happening, as you can see in the photographs. But this is what they look like. The photo on the right is showing you the stamp 2.0E. It's even giving you the engineering report number, so you can look it up. On this project, we basically just measured the extent of decay and then did the calculations on the capacity, or the remaining capacity, which of course is based on the stamp, which told us the allowable stresses, and then we determined if the decay was minor, it was probably okay, but if it was major, then they had to either replace the beam or supplement it in some manner. So just sort of a real world example of what you see out there. So that was structural composite lumber. The next group is wood eye joists, and as the name implies, it looks like an eye in cross section, similar to a steel beam. Nowadays, typically the webs are OSB material, and the flanges you can get either solid sawn lumber or LVL. And now you know what LVL is, so now you know that it's typically stronger. So if you have an I-beam with or an I-joist with LVL flanges, you're probably getting higher capacities and span lengths out of it than the solid sawn counterpart. But again, it's engineered, and the beauty is it reduces naturally occurring defects, and you get a more consistent, more dimensionally stable and stiffer product. This is from a Georgia Pacific catalog, but you can get both I-joists with LVL and solid sawn flanges in various sizes and depths, and other manufacturers make these as well. So they're available in a variety of sizes and strengths. Typically used in residential construction, I've seen it the most. They can be used in commercial, of course. Normally you see them as floor joists, but I've seen them as roof rafters as well. And like structural composite lumber, they're starting to treat these products. So if you want increased decay resistance or resistance to insect attack, you can get them as pressure preservative treated. So common theme here with all the engineered wood products, you have to find a stamp. Stamp will tell you, the properties of the product. Here's a couple examples of what you might see. And just like structural composite lumber, you can cut holes to run mechanical and so on, but there are limitations. So again, you have to go to the manufacturer's catalog, and it'll give you a diagram such as this to give you the allowable sizes and placement of those holes. So not all I-joists, these limitations will vary between manufacturers, so you need to go to the specific manufacturer for the I-joist you have to find these limitations. So as a side note, I-joists developed prior to around the 1990s, had suffered from excessive deflection when exposed to elevated moisture content, and this is primarily due to shear deflection of the OSB webs. Arnie Johnson, what you're looking at on the screen is just a little blurb from a paper that Arnie Johnson wrote. It's available on the Wood TRG, I think it was 2003. A really good paper that you can read about this phenomenon, but as I understand it, the industry has sort of recognized this issue and taken steps to mitigate it. So it's not as much of a concern for products made, post 1995-ish, give or take. Obviously, any wood product, you don't want to get wood wet and keep it wet. All kinds of things are going to happen to it, but this was an issue. So if you're investigating a building or inspecting a building, let's say, there was a fire in a house that was built in the 80s and it had I-joists for floor members and they got all soaked because of the firefighting efforts. You might want to take a closer look at those and because there is a possibility, to get excessive deflections, or if they're used over a crawl space that's not well ventilated, not well sealed, and you got a lot, high sustained moisture content down there, you can get sagging floors, due to this phenomenon. So just wanted to point that out. Again, the paper's on the Wood TRG, you can take a look. So real world example, this is that same multi-unit residential building in Jacksonville, Florida, had all kinds of water infiltration, and this picture sort of has it all. You got decayed OSB sheathing, you got decayed I-joist there, which is framing into a decayed glue-lam, which we'll get into glue-lam in a second. But something like this, the plywood or the OSB is basically gone, so that's a replacement, and the I-joist, with that kind of decay, is pretty much gone as well. The glue-lam, depending on the extent of decay, you might be able to salvage it. But this is just an example of what you'll see out there. The I-joist also has a green stamp along the web, although you can't really read it. But the point is, these things will have stamps all over the place, so it should be pretty easy to identify what you have for I-joists. All right, next product line, glued-laminated timber, called Glued-Lam commonly. Glue-Lams were developed, I think, back in the 1800s. I think it started out more in Europe, and they gained more traction here in the States, probably in the late 30s, give or take. So they've been in production quite a long time. And basically, it's as the pictures show there, it's dimension lumber laid flat, stacked up, and glued together with adhesives. And typically for southern pine, you'll see 1 3/8 thick laminations. For your western species like Doug fir, hem fir, typically you'll see 1.5 inches, although the lamination thicknesses can vary. And typical widths 2.5 to about 11 is what you see, but you can get wider. And as far as depths go, it's virtually unlimited. I've seen glue-lams 6-7 feet deep, and I know there's others that are deeper out there. So you can make really big beams out of these things and do all kinds of cool stuff like curve them and taper them, which is what these pictures are showing. But basically, the common theme with all engineered wood products is you're taking basic wood in various forms, but you're controlling the process, you're adhering them together in a certain manner, and you're creating a more dimensionally stable, stronger, stiffer product that has less naturally occurring defects, and therefore you typically get higher strengths out of it. And with Glued-Lam, you can do, again, all kinds of cool things like curve them, and there's a limitless variety of sizes and shapes. You typically see them as major framing members. Again, it's like PSL. You're not going to frame your floor of your house with glue-lams, PSLs, but you might use a glue-lam as a beam line down the center of your house, or as these pictures are showing, they're being used as big truss members or curved, tapered beams to span long distances, arches. Those types of applications is where you see glue-lam a lot. Since glue-lams can get quite long, usually the length of the beam is longer than the length of the lamination that makes up the beam. So they'll usually splice the laminations. Picture on the right is showing the most common type of joint. It's called a finger joint, and they cut these fingers into it and they fill it up with epoxy, stick it together, and there's your splice. For older glue-lams, sometimes you'll see what's called a scarf joint, which is shown on the lower left there. You don't really see it too much, but in case you do, from the side, I guess it could look like a fracture, but just keep in mind that, well, it might not be a fracture, it might just be a scarf joint. So anyways, those are the two types of joints. So to increase efficiency, when you have a bending member, you don't have maximum stress everywhere in the bending member. Typically the outer fibers will have your maximum tension, your maximum compression, but the inner fibers, at the center of the beam, in theory, you have zero bending stress. So what they do is they put different grades of lumber for different regions. So in your high tension zone, which is typically the most critical, because wood, as you know, is weaker in tension than it is in compression. So you usually have higher quality lumber in your high tension and high compression zones, and you'll have a lower quality of lumber in other zones. For like a simple span beam, you'll have maximum tension at the bottom lamination and maximum compression at the top lamination. And so that bottom lamination or bottom few laminations will typically have a very high grade of lumber to take that high tension, and then the lumber grade will get lesser in the center region of the beam. But if you have a cantilever beam or a multi-span beam, you might have, you'll have positive and negative moments. And so you might have maximum tension at the bottom of the beam in one location and at the top in another location. So this gets into, again, the layup. The layup tells you what kind of laminations you have. And there's two types of layups, balanced and unbalanced. And a balanced layup, basically, the grade of laminations are symmetrical about the neutral axis or the mid-height of the beam. And so if you had again, a two-span beam or cantilever beam, you might have a balanced layup because you need that high-tension lamination. If it's a two-span continuous, you'll need it at the positive moment region and over the interior support of the negative moment region. But if you just have a simple span, well, you only have high tension at one location, it's at the mid-span on the bottom. And so they might use an unbalanced layup because you don't have that high tension on the top, you just have it on the bottom. So this next slide will illustrate kind of what I'm talking about. The little cross-section on the left there is a balanced layup, and as you can see, the lamination grades are symmetrical. It's like a mirror image about the mid-height. And the picture in the center there is an unbalanced layup, and as you can see, it's got a different grade on the top than it does in the bottom. And usually, when it's an unbalanced layup, they'll stamp, the top of the beam as like the picture showing there with top or something to that effect. Believe it or not, we've seen stamped beams where the top is on the underside of the beam. So I don't know how you screw that up, but it does happen. And now you just change the whole. You basically change the capacity of the beam by doing that. Again, it's engineered product. You have to find some kind of identifying mark in order to know what you have. And for Glulam, you'll typically see something like this, 24F-1.8E. Basically, that number and the other information on the stamp gives you the recipe of how to make this beam. How many, if they're using number 1 laminations in the high tension zone, well, how many number 1 laminations and how many number 2 laminations, and what's the layup essentially. So that number will give you the recipe. Again, from that number, you can go to a manufacturer's literature or APA or AITC or NDS, and you can find a chart like this. And a little red box there, that's the stamp we just found. And you can read across, and you can pull off your bending, your tension, your compression allowables, from a table like this. And again, wood is orthotropic, and therefore engineered wood products have different capacities depending on orientation. So if you're bending about the strong axis, you're going to have one set of allowables. If you're bending about the weak axis, you're going to have another set of allowables. So that's what I'm trying to illustrate here with that red box. So you have to pay attention to how is the beam orientated with respect to the direction of load. And as I said, AITC provides design information, so does NDS, so does APA, so you can go to these guides and you can get all kinds of good information about Glulam. So a couple real-world examples. This is a church I took a look at a couple years ago, far outside of Chicago, but basically the church, the whole roof was essentially supported by 2 curved, tapered glulam beams. These were about, I think, on the order of 5, 6 feet deep. So they're, pretty big. And what happens with a curved beam, when the loading flattens the beam, you're going to develop a tensile stress called radial tension, and that's perpendicular to grain. And as you probably know, wood is very, very bad. Perpendicular to grain has very low capacity. And in this particular case, the demand exceeded the capacity and developed this radial tension split. I think for this one, we ended up stitching it back together with really long lag bolts, essentially. But like I said, we're gonna do a specific webinar for all these products. We'll get into more of the nitty-gritty, but I just wanted you to sort of see what they look like in real world and some of the problems that can happen with them. Here's another building I took a look at out in LA. It was a Harley-Davidson showroom. Roof was framed with curved taper glulams as well. Not quite curved they weren't curved as much as the church you just saw, but basically they had a bending failure. And the photo on the right shows you the fractures through the bottom, probably bottom 2 laminations there, and essentially just overloaded. So that's a bending failure for glulam. This is a pool roof structure here in Chicago that we're fixing. It's actually going to be under construction here in about a month or so, but they basically made trusses out of glulams. And they had all kinds of water leaks and sort of neglected it for years, and guess what happens? You get decay everywhere. So they had decayed truss members, they had decayed glulam purlins, glulam struts, and that's what the picture on the right is showing you, is that glulam purlin was so decayed it's starting, it's totally crushed in and it's starting to fail. So that's bad news, obviously. Here's another severely decayed glulam strut, which is providing bracing for the truss bottom cord. They also drilled a hole to run a conduit through your tension lamination, which, as the note says, is not smart. So these are the kinds of things you see out in the field. You need to pay attention to. Okay, so that was glulam. Next product line we're going to get into is called Cross-Laminated Timber, or CLT. This is somewhat of a new product. It was developed in Europe in the 1990s and has caught on over there. And typically we're a little bit slower here to embrace new technologies, I guess. But you're starting to see it here as well. And this is a picture of what it looks like. Essentially, it's like plywood, except instead of using thin veneers, you're using 2x6s, or which could either be solid sawn lumber or FCL. It's not just 2x6. I'm just using that as an example, but it's basically like dimension lumber or LVLs laid flat and layered up like this. Very, very similar, the same concept as plywood and OSB, just on a much thicker, bigger scale. So three ply is the minimum, but you can get four ply, 5 ply, maybe not 4 ply, but probably 5 ply. But point is, you can get them even thicker, if the strength is required. But it's the same idea. You're cross-laminating the layers, and you increase the strength, you increase the dimensional stability. And these can get quite large. You can get thicknesses up to 19 inches. You can get heights or widths of about 10 feet, and lengths up to 50. So I kind of look at it as like sort of precast construction. You can put one of these on a precast concrete construction. You can put one of these on a flatbed, bring it out to the job site, pick it up with a crane, and that can be your wall section, or your roof section, or your floor section. So that's sort of the idea. And again, you see them used as long spans and floors, walls. They can be used as a shear wall as well, and for roofs. So instead of framing a roof with 2x10s at 24 inches and then sheathing it with 1/2-inch plywood, you can maybe install glulam purlins spaced 10 feet apart and use one of these big panels to span between those purlins. So that's sort of the idea. It's got good seismic performance, good fire resistance, just by virtue of its thickness, and installation can be quite speedy and easy. And you can also get them pre-finished if you want to keep them exposed for architectural and aesthetic requirements. There's a lot of different details they use to connect these panels together. Here's just a couple, but usually there'll be a void or a let-in between the panels, or you can put a piece of plywood or LVL inside that void and attach it with screws or nails or whatever based on the the manufacturer's requirements. Again, this is just an example of how they're how they're put together and attached. And again, it's engineered, so you don't know what you have unless you could find a stamp or and figure out the grade. And this is a chart from APA, with different grades, and you can pull off all your allowable capacities, and of course it has directionality to it. So you have strong direction, you have a weak direction. So make sure you pay attention to that, and are using the appropriate allowables for the orientation of the product. As I said, APA has published a standard for CLT. It's an ANSI APA document, 320. From what I understand, it's scheduled to be included in the next edition of IBC. And the picture on the left is sort of showing you, I don't know if it's a house or what, I just pulled it off the web. But basically, they're using CLT to make their walls, their floors, and the roof. So that's, again, pretty common application for CLT. Okay, last but not least, structural insulating panels, SIP. Similar to cross-laminated timber, it's not very common here at all. I've never seen it. Again, more common in Europe, but it seems to be gaining traction, or at least you're starting to see them, more aggressive marketing. Put it that way. But essentially, it's like it's like an insulated precast panel with a core of insulating material like polystyrene or rigid polyurethane foam. Instead of concrete on the skin, it's typically OSB. So it looks like an ice cream sandwich there, but the whole idea is you have your wall, your floor. It provides structural, or roof provides your structural support and your insulating value. And a little graphic there showing you again, they can be used for floors, walls, roofs. Typically, they're marketed as having a higher insulating value than traditional construction, which would be stick framing, a pile of 2x6s and sheathing, and you build a wall. Or you can bring one of these out on a flatbed and lift it up and put it in place, and there's your wall. It's marketed as sort of a speedy construction and higher insulating value, and so on. You can get them different thicknesses. The thicker it is, the better R value or insulating value you get. And the skin is predominantly 7/16 inch OSB. Similar to cross-laminated timber, to connect them, there'll be some kind of void or let-in where you can put in this case, dimension lumber in that void, and attach it with screws. And pretty much, this is from a manufacturer called Insulating, but you pretty much have to follow the manufacturer's connection requirements, and it's available on their website. But this is sort of a very common panel-to-panel connection. As far as I know, there's no APA document like CLT has for these insulating panels. I think you pretty much have to go to the manufacturer to get loading and the insulating properties. So I'm not even sure it has any identifying marks. It may or may not, but again, it's not very common here, but it's starting to gain some traction. If you come across it, try to find out who made it and go talk to them, I guess. All right, quick summary here. We told you about structural panels. That's your OSB and plywood, structural composite lumber. That's your LVLs, LSLs, PSLs, wood I-joists, glue-laminated timber, cross-laminated timber, and structural insulating panels. And again, to summarize, wood is orthotropic, and therefore products made with wood also have different properties depending on orientation, direction, and you have to find the stamp. And from the stamp and the thickness, you can go to a variety of places like APA or like NDS or the manufacturer, and based on that stamp, you can get all your design properties for that product. So, what to look for if you come across these in the field, obviously identify what you have, and hopefully after listening to this, you have an idea what a PSL looks like as opposed to an LVL and so on. But do what you normally do. Measure the thickness. How wide is it? How deep is it? In the case of laminated products like plywood or glue-lam, cross-laminated timber, the number of plies or laminations is also useful. And how's it being used? Is it a bending member? Is it compression? Or is it tension? Or is it both? Is it like a beam column that gets compression and tension? And again, it'll depend. The design values will depend on how you're using it. If you're using it in bending, if you're using, for example, glue-lam as a bending member or as a column, you'll have different allowables for each of those uses. If they're in bold, find an identifying mark. That's the key. You need to find that stamp, otherwise you don't know what you have. And then again, do what we do. If it's decayed, measure the decay, how much, how severe, if it's fractured, so on, document all that, and then you can, come back to the office and figure out remaining capacity and how to fix it or replace it and so on. So a question I get all the time is, well, what if you can't find a mark? Well, this happens quite often. If you can't find an identifying mark, you're at a serious disadvantage, but there are a few things that you can do. If you can get the shop drawings, that'll tell you exactly what you have. As you probably know, we don't normally have an opportunity to get the shop drawings. If you can't get the shop drawings, the next best thing is the design drawings. Oftentimes, the design drawings will list minimums. For example, the glue-lams must be Douglas fir lumber. They must have a minimum bending stress of 2400 psi. They must have a minimum modulus of elasticity of 1.6, or something to that effect. So at least you have, some minimum requirements, and chances are they provided a product that met or exceeded those minimum requirements. And then if you know the age of the structure and you know those minimums, you can pull out a catalog. If it's a 1960s building made of glue-lam, you can go to AITC from around that era, and you can go to the allowable stress tables, and you can see, well, what were they making back then, and to try to essentially try to narrow down what you have. If the builder might know who supplied the engineered wood product, and they might have records, so that's another thing you can check. And for glue-lam specifically, to help you narrow it down, you can also take a sample. So again, if you know it's a 1960s building, from the design drawings you had some minimum design values, and sometimes the design drawings didn't specify a species. But if you take a wood sample, you can get a species, and then that'll help you sort of further narrow it down. Taking a species for plywood or LVLs is not really going to help you. Those are those products are rated. So whether a piece of plywood is made out of Doug fir or made out of southern pine, if it's stamped rated sheathing 3216, well, it's going to have the same properties whether it's Doug fir or southern pine. So that's not really going to help you. But for glue-lams, it can help you. So, real quick here, some pros and cons for engineered wood products versus solid sawn lumber or timber. Some of the pros, again, it's engineered, so it's more dimensionally stable. You have less likelihood of naturally occurring defects, juvenile wood and large knots and all that kind of stuff. That's sort of, you can still have some of that, but largely that sort of issue goes away. And, typically they're stronger and stiffer. I mean, again, if you're getting a really high quality, visually graded lumber like Flex Structural, it might be on par with that. But it also might be a lot harder to find Flex Structural, especially in larger sizes, but, it's not too hard to find an LVL. So that's, again, one of the pros, a greater variety of sizes, lengths. In the case of glue-lams, you can curve them, you can do all kinds of stuff. And usually, they're manufactured to certain standards, which are typically tighter in terms of moisture content. So, if you order a timber beam, an 8x10 or something, well, it's probably going to come out on site 20% moisture content, or in that range, even higher. But as opposed to a PSL, which will probably come out at a moisture content about half that. So, if that's an issue for your project, if you're worried about seasoning checks and so on from the large timber, well, PSL is a good alternative for that. Some of the cons, I understand they're more expensive. However, that could be offset by the increased strength. Maybe it's more expensive maybe LVLs are more expensive than 2x10s, but maybe you don't need as many 2x or as many LVLs to frame your floor as 2x10. So, you know, the expense might sort of work itself out. But we also find that contractors, you know, sometimes are not familiar with the proper handling techniques and installation techniques, you know, specifically cutting holes in them. You know, again, you have to go to the manufacturer and find out what limitations you have. So, you know, there's something, a little bit of a learning curve there, I guess. Some contractors are, you know, they just like to deal with solid sawn, you know. If you want some big sizes or whatnot, you might have longer lead times to get it, especially if you're trying to treat it. You know, getting treated 2x10s, you know, you can go to Home Depot and get treated 2x10s pretty easily, but it might be harder to get a treated LVL, but keep that in mind. Again, you know, just some pros and cons there.